So today we'll be continuing our lecture on DP. This will be second lecture. Today we'll cover a little bit of bitmask DP and some state and space optimization, which we talked about in the last lecture. Today we'll be mainly solving problems related to them and try to learn them from the problems. So in the last lecture, we briefly see what actually is DP and in what kind of problems we can use the DP idea. And we talked about the optimal substructure in such problems and also like about the overlapping subproblems. Like the main idea is that we have to we have to divide our problem into certain subproblems and we have to solve those problems exactly once. And we also saw that how does it help us to reduce our complexity from exponential to states below of state into transition. And like we discussed three ways in which we can implement that: recursion, memoization, and tabulation. We saw the generic idea of any DC problem, like how do we approach it. First of all, we have to define the state, then we have to write some recurrence relation, also known as the transition equation, and we have to define some wastages, and we also have to decide in which order should we calculate or should we fill the DP tables. And at the end, as per the question, you have to calculate the answer based on extract the answer from our DP states. Today we'll see a little bit about bitmask DP and also state public space optimization. Like in the last lecture, in all the problems which we solved, we saw that our state was mainly revolving around some index of the array or a matrix or something like that. But not always is that the case. Sometimes we might have to also consider a set as our state. So we'll see how we can decide that based upon the constraints in the problem, like if n is small, and we'll see that. So here are some brief ideas regarding the optimization I was talking about state and space. This idea we also saw in the last lecture about the rolling variables. Like if our state depends only on the finite number of previous states, instead of maintaining the answer across all the states till now, we can just keep a rolling variable over those states. We also see the idea of implicit dimension through a problem. The main idea is that if a DP state has k parameters and those k parameters are somehow dependent or can be related through some equation, then there is no point in just having the state of k dimension. We can rather have a state of k minus 1 dimension and we can implicitly get the kth parameter using the k minus 1 parameters of the state. We'll see this more through a problem. And we'll also see in some cases it might not be possible to reduce the state or but but we can fasten up our transitions. Like for example, if our DP is of the form DPI is of the form max or min over DPJ j less than I, then we can maintain this using some prefix max or prefix min, or we can do some range query kind of stuff. We'll see that. Or also, as it is written here in the last class, we saw calculating the longest increasing subsequence in which our transition was a bigger n. Basically, we iterated over all the indices less than current index, but we can also fasten it up to bigger n log n. We'll see that today. So that was mainly the brief intro before we start solving the problem. Does anyone have any doubt till now before we start with our first problem set? I think we can start. First problem is little bit easy, so think you all can do quickly. The problem is that we are given n positive integers and we have to split them into two groups, two disjoint groups, so that we have to minimize the absolute difference of the sum of the two groups. And the total sum is bounded by 1 in 5. We have to report the minimum absolute difference which is possible of the sum of the two groups, and each integer should go to exactly one loop. You can think about this problem for a minute or two. If anyone has any idea, you can also speak up. So your idea is that using knapsack we should always find all the reachable sums, right? And look at the reachable sum closest to total sum by two. Yeah. Basically, since we have to divide our set of integers into exactly two groups, so if we know the sum of one group is say small s, and since we know the total sum is capital S, so we already know we can get the information about the sum of the other group, which is going to be S minus S. So if we can somehow calculate all the possible achievable this value of small s, we can just minimize this value of the difference of the sums of two sets. The value is going to be mod s minus 2s, and this will be minimum about when h is s lose to s by 2s much. So yeah, we can just calculate whether which all s are achievable. So we can define our state to be that a Boolean state whether a sum is achievable or not, whether there exists some subset such that it sums exactly to S. And how will we do that? We'll do that in a knapsack way. We'll also see the knapsack problem later. Like we can maintain, suppose we have n numbers and we have processed the first I numbers, and after processing the first I numbers, we have this array reachable S, which states that which is in which the this number is true if and only if there exists some subset of first I numbers such that it sums to sums to j. So now when processing the next number I plus 1, we'll try to form the subsets involved in that I plus 1 number, and since if the now if the new sum is say some j prime, it and it since it involves the I plus 1th number, so the contribution from the first I numbers will be j prime minus ai plus 1. And if this sum is achievable using some subset of first I numbers, then this sum j prime is achievable using some subset of first I plus 1 numbers. So we'll update our state. And since our j prime depends on the j prime minus ai plus 1, so we'll transition backwards, basically from s downward to x. X is the ai plus 1, I plus 1 number, and it is the minimum sum involving any subset of any subset involving the I plus nth number. So this will be our transition equation. If s minus x is achievable, basically here we are not maintaining a 2D array saying that will ith index JSM is achievable or not. We are just maintaining this one dimension, and we are doing a transition backwards because since when we want to update our reachable s, we depend only on reachable s minus x, and we have not updated it yet. So it will be storing the information for the till the ith when we have processed the I numbers. So in this way, we can just reduce our state from n square, or rather n into s, to just s. Here space is equal s and time is equal ns. And our base case will be that an empty subset has a zero sum reachable 0 is true. And at the end, we have to just minimize our answer, which is the zero difference of the sum of the two groups, which is mod s minus 2s over all the reachable s. Okay. I hope this problem is clear. If anyone has any doubt, you can speak up. The main idea was that since we need to divide all the integers into exactly two groups, so knowing the sum of exactly one group is enough and sufficient. And so our state was revolving around whether we can achieve a sum of S using some subset. And at the end, and the transition was just like an knapsack. And we'll see the knapsack problem also later. And at the end, we just minimize our answer as per the requirement. Here's the code. You can have a look at that later. This is the next problem. This this problem is related to bit mass DP. The main idea is that the n is very small, n is greater than equal to 20, which basically gives us a hint that we can store, we can have we can have our state revolving around some subset of a set like that. We'll start in 2 or 3 minutes. You continue until then. Okay. So this problem is that we are in workers and we have n jobs to be distributed, and the cost of worker I doing job J is given in an array cost Ij, and we have to assign each, since we are in worker and n jobs, we have to assign each worker exactly one distinct job, and we have to minimize the total cost of doing all the jobs. So basically, since the number of workers and number of jobs are very small, we can just if we can if we have processed I workers and we would have all obviously distributed I jobs, if we know which jobs have been already been distributed, then for the next person we can choose among the remaining jobs. We can choose one of the jobs among the remaining jobs. So our state can be that dpi comma mass, where I says that among the first I workers, and mass is just basically a 20-bit or n-bit number in which the jth bit is 1 if jth job is assigned to one of these I workers. So dp mask, and it will store the minimum cost to distribute all the jobs which are set in this mask to the first I workers. And the and we can, but if we were to talk about some of space optimization here, is that we do not need this, do not need to store this information regarding I, since if we have I bits set in this mask, it must be the case that I workers have been assigned job. So this is just an implicit dimension. So the idea is that if if we have our workers from 0 to n minus 1, and we have a bit mask representing the set of already used jobs, its pop count, basically the number of bits which are set to 1, will tell us how many workers have already been assigned and which worker is the next one. So that index is implicit, and our state is dp mask, just the mask one, the second dimension, which tells us the minimum cost to assign the jobs which are set in the mask to the workers from 0 to I minus 1, popcorn mask is higher. And like, how will we do the transition for dpi mask? We can iterate over the job of the assigned to the I person, which will be one of the job which is set in this mask. And suppose the job is J. So among the first I minus 1 persons, mask Zor 1 left shift J. All these jobs should be distributed in the first I minus 1 persons. So this is kind of a pull DP. And what it is written here is a push DP. So I'll tell you this. We can do the transition in two ways. Suppose we want to calculate the minimum cost for DPI mask. So we can do that by iterating over all the j's, minimize over all the j's such that mask contains the jth bit. And since mask, which implies that the jth job is assigned to the ith person. So our first I minus one persons should have been distributed among the jobs. Mask depends on this state depends on this state plus cost ij. This is known as full DP. Basically, we are pulling the answer for this state from some previous state. And we can also do in this way that if we are currently at state some I comma mask, which says that we have already calculated this state, we have distributed the some certain jobs to the first I persons. Now from this state, we'll iterate over the job to be assigned to the I plus one person. Say the job is J. So this jth bit must be unset in this mask. So we can do the transition from this state to this state, dti plus 1. And since now this this jth bit also it also job is also sent to the I plus 1 person, so the mask is updated to mask draw one left shift left click J, and this state will be updated minimized by this will be minimized by dpi mask plus cost I plus 1 J. This is known as push DP. Basically, we had already the state I comma mask, and we pushed the answer from this state to the next state I plus 1 mask is or 1 left J. Both are kind of similar, but in this problem both are trivial. But in some problems, one of them might be trivial and one of them might not be trivial. Although I do not have an example right now for that case, but you'll see that probably somewhere. So you should be aware of both kind of transitions, push and pull. Is this clear? Push and pull. Okay. So here is the code, you can have a look at that. And this is kind of push DP. Basically, they have said that we are currently at the state mask, and from this mask we are doing the transition to the new mask. And how are they choosing the mask? They are choosing the job which is not assigned to any of the workers, and they're minimizing that particular state. Okay, this one is the knapsack problem. This is simple, so I'll just do that quickly. It says that we have an item which is the weight wi and value vi, and the knapsack capacity w, basically the total items which we can have in our knapsack their weights can sum at most w, and we have to select subset of items in order to maximize the total value. And so, and we had the first problem kind of very similar idea. Rather, I should have done this problem. Okay. The If the naive idea is that we can have a table dpij which says that we have processed the first I items, and the subset which we have chosen, the weights of those items sum up to j. What is the maximum value which we can obtain? And the transition would be that if we have chosen the ith item, then we know that from the first I minus 1 items, the weight would be j minus wi. And if we have not chosen the ith item, the weight from the first subset of the first I minus items would also be j. But also here we can do the same optimization that since our dpij depends only on dpi minus 1 something, so instead of having a space of big N into W, capital W, or rather summation big O N into capital W, summation Wi, we can have our space to be just big of W, capital summation Wi. The state is that dpj is the maximum value achievable with exactly the capacity j, and while doing the transition, we have to take care that we just do the transition from backwards from the weight capital W down to small w. Otherwise, we'll just do the wrong transition because dpj depends on dpj minus w. So we should not have updated this state before we are updating this state because we are just not maintaining the first dimension. So that's the only thing we have to take care of while we are doing the space optimization. In the base case is that the maximum value achievable is 0 for all the gates, and the answer is CPW. This problem is just beyond because it was quite similar to the problem one. Yeah. So this one This is also related to bit mass DP, similar idea. Okay. So I'll just quickly do the speak up this solution because I'm recording this. So we are given that we have n cities and we are also given a distance matrix which basically which will tell us the distance between the I city and the j city, and we have to find the shortest close to that starts at the 0th city and visits every city exactly once and returns back to 0. So we, we only care about the path starting from city 0 and visiting every city exactly once. And suppose we have visited subset of cities. Now we need to move to the next city. So while doing that transition, we only care about the last city in our path. So our state should have some information about the last city on our path. So a state is basically, and we should also know which cities we have already covered because we need to visit every city exactly once. So a state definition is that DP mass class is that the shortest path starting from 0 covering all the cities which are set in mass, and our last city is the last one. And we can again do a push kind of transition for we can iterate over the next city which is not already visited, and we can just update the new state DP mask or one let's say the next, and the last city is next, and the cost would be moving from last to next. And this case would be we have already only covered the 0th city and the last city is 0 and the minimum cost is 0. And answer is that since we need to our path needs to end at 0, so we can basically just do that. We have like the just from the just before the we visit 0 again, we must have visited all the cities and then we would have visited the 0th city. So we can just iterate over the last city before 0, and our mask should be the complete mask, which basically tells us that we have already visited all the cities, and we can just minimize the answer over this moving from the last city to 0. The subproblem was fully described by the which cities we visit, which we have already visited, and the last city that were enough to solve this problem. So our state was revolving around that. This is the C++ code which you can have a look. It's simple. This is the next problem. This is also quite similar a bit mass problem. Here the constraint on n is not small. The constraint only on n is small. We are given an n by grid in which some of the seats are usable and some are not, and we are told that a student can copy from a neighbor immediately to the left, right, left, or upper right. Basically, student sitting in the cell I comma j can copy from student sitting in the cell I comma j minus 1, I comma j plus 1, and I minus 1, j minus 1, I minus 1, j plus 1. And we have to occupy a maximum number of students with no possible copy. So as we can see that the number of columns are small. Basically, in a row, the number of seats are bounded by 10. So if and the only constraint in student sitting depends only on the current row and the previous row. Like we don't care about how a student is sitting in the row which are two at a distance of 2 or more behind us. And since we can't copy from them, so if we can just somehow store the information regarding at what seats are students sitting in the previous row, then we can just calculate the maximum number of students sitting. And for the current row, we just need to ensure that there are no two consecutive students sitting. So a state would be that DPR mask is the maximum number of students sitting in the first R plus one rows with the and we should and we know should know the sitting of the students in the RF row. And again, since we only care about the previous row, so we can remove this dimension. And a valid mask would be that there should not be any two adjacent bit sets, And we can do the transition from the previous mask such that if ith bit is set in the current mask, then the I minus 1th and the I plus 1th bit should not be set in the previous mask. So if we shift our mask left by 1, then it should not have any common bit with P. And if we shift our mask right with 1, it should also not have any common bit with P. So from all such previous mask P, we can do a transition to the current mask M. So I'll just write that dpr mask can be basically be known from dp r minus 1 comma p. dpr minus 1 p basically has the information of the maximum number of students sitting in the first r rows such that the occupancy of students in the r minus 1 row is given by this mask. So if the mask is valid, basically it satisfies this, and this mask is also valid such that no two adjacent seats are occupied, then dpr mask can be maximized with this plus the number pop count of the mask. And the base case would be that in the like in the first row, if no one is in the first row with all valid mask like dp0 mask, student sitting in the 0th row with mask m, if mask m is valid such that no two adjacent seats are occupied, this is just equal to pop count of mask. And answer would be the maximum over all the valid masks of the student sitting in the last row and minus 1 row. I think you also clear. This is also similar. Yeah. In this problem, we are given that we have n people, and we are also given a list of incompatible pairs, and we have to partition everyone into minimum number of groups such that no group contains an incompatible pair. Basically, we need to assign every person to some group such that in a particular group there should not exist two persons so that they form an incompatible pair. And we are given that the number of persons are at least 16. So this also gives us an idea that we can have a state revolving around the groups, the number of each person which have already been assigned some group. All this problem, which first of all we like to tell about how we can get over all these submasks in devotee to the end. Like for all the numbers in the range from 1 to n, if we want to iterate over the submask of them, then we can just use this technique. And this way we just iterate over we can iterate over exactly the submask of the mask of this mask in descending order. Typically, we start with the mask itself, and at every step, until our submask reduces to 0, we just move to the very next submask of the mask in descending order. And why is it so? Suppose the mask, submask of the mask sub, say it has the 0th bit set to 1, basically it is odd. So the very next submask in the descending order would have this bit set to 0. So it will just do a -1, and when taking AND will be masked, all the bits will be preserved. And suppose if this bit is not 1, this bit is 0. So consider the first lowest bit, which is 1. All these bits would be 0. And since this submask is also a submask of mask, and when we'll do this -1, what would happen is that this these all bits would be set to 1, and this bit would be set to 0, because on doing +1 on this will it will reach here, right? And since all these bits were also present in the mask, because it was the submask of mask, when taking AND with the mask, all these bits will be removed, and we'll get the all these bits will be preserved, and only the bits which are present in mask will be retained, and we'll get the very next submask of this mask in the descending order, because the prefix is the same, right? And you can prove that this is ordered Euclidean, because for each mask you can just calculate the number of submasks, we iterate over all the submasks for each mask. If a mask has k bits set, there will be 2 to the k submasks. Like a bit can be set or unset in a submask, and you can just take the summation over all 2 to the k. You have to just count the number of numbers which have exactly k bits set in this range, and you can get that this is 2 to the n. I hope it's correct what I said. Did you get it? Like I'll just show you the proof. So since I told you that using the inner loop, we'll be iterating over only the submask of the mask, not any other number, right? So basically this entire loop in, okay, got it. If anyone did not got it, we can just read over it. It's done here. Basically we just have to count the number of, this is the complexity of this is just equivalent to the total number of submasks of all the numbers in this range from 1 to n, and which we can calculate by enumerating the number of bits in the number, we said k, and the number of submasks will be to the k, and the number of such numbers n to k, and that's t to the n. Okay, so coming back to this problem, since we need to divide our persons into certain number of groups, and so we can, so if we can if we know that we have already divided certain number of persons in some groups, in some minimum number of groups, such that there is no conflict between them, if our state is around that, then we can probably do something like our state can be good of dp of mass, which says that we have what are the minimum number of groups in which we can divide all the persons in this mass, such that there is no conflict there's no internal conflict in any of the groups, and we calculate this. So since we have this mask, and we'll know that we need to divide certain number of persons, say P1, P2, P3 till Pn, into certain number of groups. So consider the group involving the first person, the bit which is lowest bit which is set in this mask. Consider the group of that particular person. So we need to that the group of that particular person should be a submask of this mask, and it should also have the lowest bit set. Or we can also have look over the person, the last person, whichever is convenient. So if we can form the group of that person, then suppose the group of that person can be represented by a submask S. Then if that group is valid, first of all, we need to check if that group is valid or not, which we should pre-compute about, we should pre-compute whether for every mask, whether that mask is valid or not. How do we pre-compute for a particular mask? Like we can't just think about we have to pre-compute, we have to start thinking in this way, in this order, and then we'll know that we also need to know whether a mask is valid or not. That will need a pre-computation. So for this mask, how do we know if this is valid, which we can pre-compute for a particular mask? Just for each person, if we know that if we for each person, if we can have a mask of a persons with which it is not compatible, and then if we can if those two masks share a bit, then this mask is not valid, right? Like for example, if we have any mask m, if the set bits are b1, b2, b3, say bk, and for the BIF person, we have another mask from the input which contains all the persons which are incompatible to this person. Suppose the mask has the bit set C1, C2, C3 says Cn, and we need to check whether this mask is compatible or not. So for each BI, we have this mask, say MBI. If MBI and M have any bit common, then this mask is not valid, right? Otherwise, this mask is valid. So it is just for each mask, we can do this in big O number of bits to check. When this also not does not need a computation, we can just do it on the go. For each mask, we can check if we have formed this particular mask MBI for every person from the input. Then we can do this in big O of number of bits to check whether a mask is valid or not. And once we know whether a mask is valid or not, we have a submask involving the smallest person, then we can just check if this submask is valid. Then for the remaining persons which are represented by this mask, we would know the minimum number of groups in which they can be divided, and we can do the plus one to that. So good of mask is basically set to one if this mask is valid or not, and DP of mask is the fewest valid groups in which we can divide the persons in that mask. How do we calculate the DP mask? Is we iterate over the submask such that it contains the lowest bit. Basically, we are iterating over the subgroup of the person which is with the least index, and we check that if that submask is good or not. If that is good, then we have one group for that particular persons which are in this submask, and for the remaining persons which are represented by this submask, we have computed the minimum number of groups. And that's why we need to iterate over the submask of a particular mask, and we can't just naively do a 2 to the n into 2 to the n, 4 to the n. That would lead to a TLE probably for n equal to 16. That would be 2 to 32, which would be greater than 1 So we can't just iterate over all the masks and then again iterate over all the masks and check if this is a submask of this mask or not. We have to do this in this way only. This is an efficient way to iterate over all the submasks in order 3 to the n, as we saw the beginning. And base case would be that the minimum number of groups for no person is 0. Answer would be for all the persons for basically the full mask, the minimum number of groups which we would get after running this TP. Is this clear? Or should I tell you something again? Well, we have a lot of time if you want. I can just do that again if some part is not clear. Should I? Okay. Useful. The solution is written if it is not clear to you until now. The code is also there, and I've told the major part about the trading only formulas. You can also read about it from the website I opened. The next problem is finding the longest increasing subsequence in big O and log n rather than not in big O and square, which we did in the last lecture. This probably many of you would know. Do you? In the last lecture, the idea was that we were storing the length of the longest increasing subsequence ending at the index I, for which we were iterating over all the indices j less than I. And if they satisfied that aj was less than ai, then we were doing the transition dpi equal to dpj plus 1. We were maximizing this with this, but this one's bu n square. This is bu n square. And now main idea is that if when we have processed the first I elements, when we have processed the first element, among all the subsequences, among all the increasing subsequences of length j, we only care about the subsequence with the least last element, because suppose a subsequence of length j is a1, a2, say aj, cyclically increasing, and another subsequence is b1, b2, say bj. And if aj is suppose less than bj, then if there exists a increasing subsequence of a larger length involving this prefix, then we suppose this can be extended to with some element c. Then the claim is that this subsequence can also be formed a same, since we only care about the length of the longest given subsequence. A similar length sequence can also be formed with this prefix. Since c is greater than bj, c is also greater than aj. So the main idea is that among the first, if we can somehow maintain this array, that what is the smallest element which which can be an last element of an increasing subsequence of length j. Is this idea clear? Why do I have this idea? And the main property is that if I have an vector, if I have an array in which at the ith index I'm storing at the jth index I'm storing the smallest element, which can be the smallest value of the smallest element, which can be the last element of a strictly increasing sequence of length j. Then the claim is that this array will be non-decreasing. Why? Because suppose we can prove this by contradiction. Suppose I have processed I elements and consider two indices of this array, index j and index k, and let us name this array as b. And if bj is greater than bk, this implies that there exists the smallest element. Bj is greater than bk, right? So consider this LIS, longest increasing strictly increasing subsequence. Then since this is of length k is greater than length j, so consider this sequence b1k, b2k, bjk. So the jth element of this sequence is definitely smaller than this bj. So this array is not correct, right? So this array is this array is non-decreasing. And once we have this property, then we can update this array easily via a lower bound or a binary search, which makes the transition below any log n. That's the main idea. So we have an array tails tail, which is storing the smallest possible tail among all the increasing subsequences of length k plus 1. And this array is sorted as I proved. So we can binary search, find where the current element can fit, and we replace the first element, which is at least x. And we drop our transition from n to log n. So, and since there are n states, so it is n log n. And you can have a look at this code, how the transition is happening. This is the main idea behind this. We'll do the last one. This is this is a bit better version of the knapsack problem. In this, we have we are given that for each item, we also have some quantity c, and we are allowed to take 0 to c copies, and we have to maximize the total value. Now, we just can't do a DOW into c and n into w into c solution, because that would just kill it, right? So main idea is that for any item which if it has a quantity c and we are taking x copy of that. Then if we just change this WVC to equivalent items W, comma, having weight, like if you can just replace this quantity cap C from C to we can have corresponding items having the weights, one times W and value 1 times V, 2 times W, 2 times V, and so on and so forth, up to the power k W to the power k V, and then the remainder R times W, and R times V. The claim is that any number x in sense can also be achieved by using some subset of these items, and these are log many items. So our time will reduce to W times log Ci, something over log Ci. And why is it so? Consider any number C and consider its finally representation. The MSV say at the q plus 1 of k, and consider it to be 0 to k, and the number 2 to the k plus 1 minus 1 is 3 lesser than C. So we have these items 1, 2 up to 2 to the k, and the number C minus 2 to the k plus 1 minus 1 is our R. We have this item corresponding to that, so these all sum up to C, and consider any x. If x is less than 2 to the k plus 1 minus 1, then we can just choose the items corresponding to its final representation. If x is actually 2 to the k plus 1 minus 1, then we can just first of all choose R, and then we can move R from it, and it will be less than 2 to the k plus 1 minus 1. Then we can choose the corresponding items corresponding to the final representation. So that's the main idea. We'll split the items. Instead of having this weight, value, and capacity, we'll just split it down into normal items, having weight and only weights and values. And for each C, we'll have log C items, and we'll just do the normal map. Here we are just there in the code, as you can see, we are splitting the items first. We're taking the of the remaining item C and K. K is basically some to the power X less than equal to C, and we are creating the corresponding item with weight and value, and then we are just running. So that's it for today. We saw 8 problems involving Bitmap BP, knapsack optimization, and log solution for LIS. And